Hello, today I'm going to be teaching you how to solve systems of nonlinear equations. So here are a couple of prerequisites before you start this lesson. First, you should know how to solve linear systems of equations. Then log rules, trig identities, and the quadratic formula are also things you should brush up on. Great, so what are the different types of nonlinear systems? Well, there are lots of them, but here are some of the main ones. Radicals, logs, trig, reciprocals, and exponents. For this video, I'm going to focus on radicals, trig, and reciprocals. I'll cover logs and exponents in their own video later on. Okay, great. So here is our first problem, taken from the CMC 2016, question 8.3. Determine the pair of real numbers x, y, which satisfy the following system of equations. So before I get started, and this applies to all of the other questions as well, I really suggest that you pause the video and try figuring it out on your own before actually watching the answer. Okay, so for this system of equations, clearly it can be classified as a reciprocal system, right? Because there are reciprocals of your variables in here. 1 over x and 1 over y. So the key insight for solving these sorts of problems with reciprocals in the systems is by introducing a substitution so that you can convert this into a normal linear system. And how do we do that? Well, we can say a equals 1 over x and b equals 1 over y. And conveniently, this allows us to rewrite the system as a plus b equals 1, 2a plus 3b equals 4, right? And this looks very much like a normal linear system of equations that you would solve with substitution or elimination. So, from here it's straightforward. I'm not gonna solve the rest of the problem. You can double check your work if you want. The solutions are posted online. And yeah, let's move on to the next question. So this is taken from CMC 2006, question A4. Determine all solutions x, y to the following system of equations. For this one, it basically adds on to the one that we just did because, it still has reciprocals. However, instead of y, it's y squared. So it's going to be a tad bit more complicated. However, the basic trick remains the same. Instead of 1 over x, we're going to add the substitution so that a equals 1 over x. And now you might guess that for your b, we're still going to do 1 over y. We're just still going to substitute b equals 1 over y. Unfortunately, this will not work. Well, it will work, it's just that it'll be much more complicated. There is a way to do a substitution so that instead of having exponents and stuff in there, you can straight up make it a normal linear system of equations. And the key to doing that is to say b equals to 1 over y squared. What this means now is that this system becomes 4 over x is just 4a plus 5 over y squared is 5b equals 12. And the bottom equation is 3 over x, which is 3a, plus 7 over y squared, which is 7b, equals 22. And there you go. We've got ourselves a nice linear system of equations using this substitution. So this is the second problem that we've solved. From here, it's just trivial. You can just solve the system, resubstitute your values back in, and get all solutions x, y. The reason it's all solutions, not just one, like in the other question, is that you have a y squared, meaning that you're going to have to take the positive and negative square root of both sides. Just to recap before we go on to the next question now. Basically, anytime you have some sort of reciprocal in your system of equations, try doing a substitution, such as a equals to 1 over x, so that you can get rid of that reciprocal and hopefully end up with what looks like a normal linear system of equations. So anyway, moving on to the next question. This is from Euclid 2017, question 7b. So this one is a bit more complicated, so I'm gonna build up to it with another question. It's not really a question, it's just more of, I want to show you a trick that you can use to solve this question. So let's say you have root a plus root b equals k, which is a number. A plus b equals q, which is also a number. And you're trying to find the value of a times b. How would you approach this? Try, thinking about this by yourself for a couple seconds, and when you're ready, come back. So the trick is, whenever you come across an equation with radicals in them, especially when it's a radical added to another radical, in this case root a plus root b, try to take the square of both sides. What will happen? In this case, you end up with a plus b plus 2 root ab equals k squared. And conveniently, a plus b is just q from our second equation, right? So what were we trying to find in the first place? Well, ab, which is right there. So if we isolate ab, we can do that by saying 2 root ab equals k squared minus q, because I just bring that over, and divide both sides by 2. Finally, square both sides, and you have your answer. You have a times b in terms of k and q, which are just numbers. So this is a very interesting trick. Let's see if we can apply this and how we can apply this to this next question. Determine all pairs AB are real numbers that satisfy the following system. Root a plus root b equals 8. Log base 10a plus log base 10b equals 2. Okay, so first of all, log base 10 is just, I'm just going to write it as log to make life easier. And also that's because that's convention. Alright, so just going off of that last example that I did, it might just immediately jump out at you that root a plus root b equals 8. It's as if it's almost asking you to square both sides, right? So let's do that. Root a plus root b squared equals 8 squared, which is a 64. The left hand side is a plus b plus 2 root ab equals 64. We can't really do anything now, right? But okay, let's move on to the next equation then and see if we can manipulate that. Log a plus log b. If you remember from your log rules, this is the same thing as log ab. Okay, well that's amazing, because if you look here, we have ab there, we have ab there. So let's try to isolate ab from our second equation. We can do this by taking 10 to the power both sides. Because 10 and log base 10 are inverses, that just cancels out. And we're left with ab equals 100. There you go. Great. Okay, so now we can go back to our other equation, plug it in, and we end up with a plus b plus 2 root 100 equals 64. And if we move this over to the other side, a plus b equals 64 minus 2 root 100 is just 64 minus 2 times 10, which is just 44. So now we have two equations that are much more simple looking than what we had previously. Before we had a bunch of radicals and logs and other complicated stuff. Now we just have a plus b equals 44 and ab equals 100. Okay, so how do we solve that now? Because it's still not a linear system, right? However, it's close enough. We can use substitution to figure it out. From this equation, solve for a. Okay, plug it into this equation, our second equation. So we get 100 over b plus b equals 44. Now this, in disguise, it's basically just a quadratic, because let's see what happens when you multiply both sides by b. Left hand side we get 100 plus b squared. Right hand side we get 44b. If we rearrange the terms a bit, this is ripe for us applying the quadratic formula, right? This is amazing, because all you have to do, use the quadratic formula. You get two values of b, and for each one, substitute it into this equation to find the corresponding value of a. So you're gonna get two pairs of answers, a comma b. So yeah, this one was a bit longer than some of the other examples we had, so I'm just gonna quickly recap. We started with these two equations. We noticed that this is a radical equation. We should probably square both sides, and we did. We get something interesting, right? For your second equation, we used a log property to deduce that ab equals to 100. Then we resubstituted it back into our first equation. Okay, we simplified a bunch, and we get a plus b equals 44. Now, a plus b equals 44, ab equals 200. This is much easier to solve as a system. We can use substitution. Eventually, we end up solving a quadratic using the quadratic formula. Great. So, next, we have a question from the CUMC. Here, let me just raise this up a bit. We have a question from the CUMC, 1996, question A10. Okay, so the question states, determine the sum of the angles a comma b, where a and b are between 0 and 180 degrees inclusive, and yeah, this stuff here. So sine a plus sine b equals root 3 over 2, and cos a plus cos b equals root 1 over 2. How do we solve this? Well, first of all, we're in this lesson, we're going to do a simplified version. Instead of finding a plus b, as they want us to do, determine the sum of the angles, we're just going to find a minus b and call it a day. The reason for that being is that going the extra step from a minus b to a plus b is a bunch of extra work that isn't really related to, what I'm trying to cover in this lesson. Also, if you really want to go all the way and solve the question as it is, I'm probably going to make a write-up of the solution and post it on our website soon. Okay, anyways. So, what do we have here? This is not a reciprocal system. This is not a system involving reciprocals. This is not a system involving logs or radicals or anything like that. This one has trig in it. So, the key insight for systems involving trig is that you want to find a way to cancel stuff out using the trig identity sine squared of some angle plus cos squared of that same angle equals 1. So we want to find a way to use this. That's the key to these sorts of problems. And clearly these have sine squareds in them, cos squareds. In our equation, we only have sine A plus sine B, right? So the first step would be to just square both sides. Okay? It might seem random, but bear with me. Let's just go through the algebra. So sine A plus sine B squared equals root 3 over 2 squared. So that's just 3 over 2. Okay? The left hand side simplifies to sine squared A plus sine squared B plus 2 sine A sine B equals 3 over 2. Our second equation, let's square that now. I'm going to do it in a different color. Let's square that now. Okay, so cos A plus cos B squared equals root 1/2 squared, which is just 1/2. And so the left hand side simplifies to cos squared A plus cos squared B plus 2 cos A cos B equals 1/2. Now, at this point, it doesn't really seem obvious how we could use the Pythagorean identity, right? None of the equations have sine squared plus cos squared. But notice, this one has a bunch of sine squareds in it. This one has a bunch of cos squareds in it. So let's just add them up, and hopefully some stuff will cancel out. right? So let me just erase some of this stuff. So let's just add them up. Okay. So first of all, sine squared a plus cos squared a, that's just 1. Amazing. Okay. So we've used the identity and managed to cancel something out. Cos squared b plus sine squared b is also 1. Perfect. And then let's just add the other two terms. I'm going to factor out a 2. Sine a sine b plus cos a cos b equals 3 over 2 plus 1 over 2 is just 2. So notice 1 plus 1 cancels out with the 2. We're just left with 0 on this side. And then we can divide both sides by 2, right? We're still left with 0 on the right hand side. And therefore, we are left with sine a sine b plus cos a cos b equals 0. And now, this should immediately jump out to you as cosine of a minus b. This is one of the angle difference formulas. It's literally this definition. Okay, so yeah, you might like memorizing your trig angle addition subtraction formulas is a key way to do well in math contests because it just opens up so many techniques to you, such as this one. So we can just substitute that in. Cos a minus b equals 0. Perfect. Now remember, what do we want to find? A minus b, right? And so we just take the inverse cosine of both sides. Right? A minus b equals the inverse cosine of 0. From there, we can use some logical deduction because a and b must be between 0 and 180. And yeah, we can deduce that a minus b equals plus minus 90 degrees. And that just about concludes this question. It concludes my lesson, rather. Hopefully, you enjoyed it, and see you in the next lesson.